very nice the opportunity to show what I thought about the cosmic rays, particularly after the discovery of the pevatrons by Nozzle. So my title here is the high energy cosmic rays, questions and approaches. First of all, let's review on the scientific questions. Of course, we know the cosmic ray is very important, particularly because the highest energy of cosmic rays is already reached to the 10 to the 20th. By this figure, you can see this is, the energy is already reached very high. And also we measured so many species of the cosmic rays, including photons and the electrons and positrons and antiprotons. Why it is so important, need to see, because the energy is so high, comparing with the LHC at the energy of the 10 to the 13th EV for protons, the energy difference is already 7 orders of magnitude. But we still have the question about what the cosmic ray is, where the cosmic rays come from, and probably the most important question is how those particles can be accelerated at such a high energy. To me, if we want to systematically study the problem of the origin of the cosmic rays, I think we have to go through this at least this 4 steps. First of all, we try to get the best information from this high precision measurements of the pevatrons of the very high energy sources. For example, like this one is already published in Nature as the source. This is the very famous 1908, GA 1908. And also for the pulsar wind nebula, like a Crab nebula, we already have the very beautiful measurement of the spectrum like this, cover the energy from the very, very low to the PeV already. So we try to build a model to understand this kind of the thing. So the second step, of course, we have to do the identification of the acceleration and irradiation mechanisms and the phenomenological study associated with this kind of source, okay? And then I think it's a very important step is to try to understand the cosmic rays we measured on the ground, on the Earth. So we have to do the phenomenological investigation of cosmic rays transportation in the regions nearby the source, and also the interstellar propagation, and even the very nearby to our source, to the Earth. We have the interplanetary space have to deal with, for example, like the anisotropy and such things. So in the end, once we have this kind of the spectrum theoretically and experimentally understand this cosmic rays behavior, then we have to measure the spectrum on the ground with the very high precision to try to understand, for example, like the structure of needs. Let's just give the example we probably can reach within a couple of years. So seems to be that everything is essential. For example, like a high precision measurement and also very careful phenomenological study of the cosmic rays. Now let's see what is the preliminary answers from Nozzle already reached. Here I just show you the map of this map is sort of old already. This map is published in May this year. What we saw from this map is we found 12 very beautiful sources lined up in the plane of our galaxy. And to give you the idea about the Crab nebula here, you see, the problem is our angular resolution is only a 0.3 degree. So for such a very compact source, we can see just like this spot. Okay. But something that's really interesting is that those pelotrons actually, we see a very much actually coincidence with the already known TeV sources. This blue circles represents all of this TeV sources in our galaxy. Of course, we saw something new as well. For example, like this guy doesn't have the counterpart of the TeV gamma ray emitters. This is the first thing we know now by using Nozzle within 1 year. Okay. And then let's see what Lasso is. Lasso is the gamma ray telescope, first of all. And this the area of Lasso is 1.3 square kilometer, and filled up with 2 types of the detectors. You see this kind of a white dots here. Each one of this is scintillator detectors. And totally we have 5,216 of them, make the grade of triangle grid with the spacing of 15 meters. So fill up uniformly this region. Those guys can measure the arriving time of the secondary particles. Eventually we can use this information to build up the direction of the shower. And we can measure the energy by using this the total number of particles of the shower. Most importantly for Lasso, we have 1,188 muon detectors, but you cannot see it because that is underneath these humps. Each of those hump has under this hump we have a 7-meter diameter water tanks. The water tanks are muon detect because we have the coverage of 2.5 meters of dirt on top of this detector, on top of this tanks. So only muons can penetrate it down to this tank. Then the water chunk of the generated inside of the tank with a very high reflectivity of internal material, then that makes this muon be measured. So here give you the idea how big of a 1 PeV photon event looks like. This is the whole array, and this 1 PeV event looks like this. Okay, this event had actually detected with only the half of the array, just like this. So some part of this shower actually missed. Now with the whole array working like this, we will have a much more complete measurement of this shower if it happened again. So the energy range for this detect is covering of 0.01 to 10 PeV for gamma rays. Now this detector is already finished and actually operated, started from July of this year, and the altitude of this area is 4,400 meters above sea level. Because of its muon detector, this detector Nozzle becomes a very, very clean gamma ray detector. Here, I just give you the idea how strong this power, the rejection power is to get rid of the cosmic ray background. This is the number of muons measured by this underground muon detector array, and this horizontal is the number of particles measured by the scintillator counters. If you put these 2 variables correlated to each other, you see this blue population is generated by proton shower, and this pink population is generated by gamma rays. So there is a very clearly separated. If you translate this into the spectrum, this is actually measured the cosmic ray spectrum as the function of energy. This energy is reconstructed using this number, okay? So this is from a Crab direction within the 1 degree here. It's a very small space region. And then if we use the cut, very simple cut, just like this number versus this number, if this ratio must be less than 1/230, then we got rid of cosmic rays. How much? At the 100 TeV, this rejection power is something around 10 to minus 4 from here down here. At about 500, above 500 TeV, this rejection power becomes 10 to minus 5. This spectrum measured becomes like this. And then if we use the gamma ray spectrum measured from the parabola direction, this is the prediction at the moment, because at the moment we didn't have the 1 year measurement yet. So this is the actual spectrum of gamma rays from the parabola. Depends on what the fitting we use. This is the log parabola, and this is the power law, I think. So give you the idea. This is sort of clean, background-free measurement, because the cosmic ray, the gamma ray signals is already 1 order of magnitude higher than the cosmic ray background rate. Okay, so this is very powerful. And in the center of the array, let's go back to see here we have a very big warehouse. This warehouse is not filled with goods, but it's filled up with water. 5 meter water is inside this area. The total area of this detector is 78,000 square meter. And filled with the PMTs like this. This is big, very big PMT. There's 20-inch PMT plus a 3-inch PMT to make the whole dynamic range to cover it. And the spacing between this sets is about 5 meter. So in total, to cover this area, we have 3,120 of these seals recorded. And it here give you the idea how something like a few TeV gamma rays will generate such a shower inside of this warehouse. Here we call the number 1, number 2, and the number 3. So now this shower just shows us here is the core of the shower, and all 3 detectors respond to this shower very uniformly, and then we can use them to reconstruct the energy of the shower and the direction of the shower. Very interesting. If you look closely, this kind of shower is very compact, but for the showers generated by cosmic rays, we have many this kind of isolated, very bright spot outside the core region. Those probably generated by muons. So we can use this kind of number, how many this kind of isolated, very bright spot versus the whole shower, then we can do the rejection of the cosmic ray background as well. This energy range is lower. Basically, is from the 100 GeV to 10 TeV. So this is a survey detector. The goal for this detector is to find many sources to do the surveying. Now, another very exciting results, of course, is coming from the from the parabola. This parabola at the moment that serves as a standard candle. We have to measure the parabola with the very high accuracy of pointing direction, and also because this one is very, very compact, so we can use. We know this is a very it's a point source, so we can use that to measure our angular resolution, basically the size of the spot. Okay. This result is coming from, we call this KM2A, just the scintillator array plus the muon detectors. So by using this high energy detectors, we measured angular resolution is about less than 0.3 degree. The energy is above 25 TeV for this map. So this is the measurement basically you see from the from September to July. It's less than 1 year, and we have this sensitivity for this detector. The water chunk of detector in the center of the array is more sensitive, and the energy range, of course, is lower at above the 1 TeV. You can see it, the spot becomes smaller. So this detector has a better angular resolution. Both detectors arrays give us a very nice pointing accuracy. This actually is better than this, something around the 0.03 degree level for both detectors. We have also accepted these two sets of arrays. We have 18 telescopes as well. Those telescopes are very small. The size of the mirror is something about 5 square meters only. So this originally is designed for the cosmic ray measurement at a very high energy, basically above 100 TeV. However, this detector has the field of view. Each one of these guys has a field of view of a 16 by 16 degree. Now, by using the 18 telescopes, we can make the full circle of the coverage between the zenith angle from centered at the 45 degree in the center part. So with this 16 degrees coverage, all of this 12 penetrons, actually every night we can measure. For example, like this black part is the part of the trajectory of this guy in night. So for example, like a crab will passing this mirror, and 1825 will go through almost all the way in the night. You see, can be seen by a couple of mirrors. So that gives us the chance to make a cross-checking. For example, this is the very famous event around the PV photon from the crab nebula. This actually published in Science already. This guy is measured not only by the ground array here, very beautiful. Simultaneously, there is one telescope at here actually looking into this direction. Very lucky. This detector actually is working in the time when this event reached the Lasso. So this is the imaging measured by this mirror. Looks very thin, and we can use this chunk of detect and ground array to do the energy reconstruction and make the cross-checking. You see, if we use the chunk of telescopes, we get the energy as 0.9 plus minus 0.2 PeV of this event. If we use the ground array, we have almost 400 detectors being triggered, and the total number of particles is about 4,500. And we got an energy as well, equals to 0.9 plus minus 0.1 PeV. And this event is really clean because you see in this event, we have these circles represent the muon detectors. We have only 11 muon detectors being hit with 15 muons. So this is get a very clean measurement. And the chance probability of this event being a cosmic ray is less than 0.1%. So this 18 telescopes, basically we can make the energy measurement. Also, we try to use the multiple parameter measurement to get the composition down well enough to try to separate the proton spectrum, for example. I'll talk this later on. So for the galactic VHE, UHE, we define this UHE is actually the energy above the 100 TeV on gamma rays observation. So this is the sensitivity of LHAASO comparing with other detectors. For example, like this is CTA here, above 10 TeV or 20 TeV, this detector is really sensitive to try to do this. And also this part is from the water Cherenkov detector in the center part. So because this is the almost a 2 pi space to be covered and then working 24 hours per day. So this is a very powerful surveying detector. The energy coverage now is approved, has already covered up to 10 PeV. The surveying sensitivity with a very large field of view. So we hope this kind of cosmic ray accelerators, for example, like pevatrons, will be at the order of this number within a couple of years. Currently, actually, is much more than 12 already. By using these detectors, we can measure the spectrum as well, just to show this as before. So you see, once we have such a very careful measurement of the spectrum, this part is by LHAASO and this by Fermi. And if you want to use a very simple model like the one-zone leptonic model, you look, seems to be working well, but if you looking very closely, you see that the deviation from the model actually is quite large. So that's require the very precise measurement of the spectrum. With such a high statistics, if you look at closely, this part, probably the one-zone model is not enough. We saw certainly some deviations here, you see? If you look very closely, once you put the proton the contributions inside, then we can make this fitting actually much better. If we look at the above 1 GeV level by using this lepton plus proton model, now the situation is much better improved comparing with this. You see this kind of deviation being improved like this. So that means once we have this kind of very precise measurement of the spectrum for this kind of source, which is very, very simple, just basically point source, then we can do quite a good job in this kind of mechanics study. So the accelerations of this galactic pevatrons is going to be a question within a couple of years for LHAASO. We try to make them about 550 TeV. We're going to use this detector, which already reached the sensitivity at this level. So this is a very very sensitive detector. Even the angular resolution still is something like a 0.3 degree level we already saw from the Crab measurements. But we think we can do quite a bit of a morphological study already, because all of these 12 pevatrons actually are very extended. Some of them is really extended to a couple of degrees level. So at least we have some idea now about those pevatrons. If you look closely, you will find all of these 12 sources actually it's not only, for example, like pulsar nebula, but also something very interesting from this young massive cluster, star clusters. And actually, there's something very interesting. If you look on this list, we very rare to see SNRs with a very high energy. Probably, this SNR is still the very main source of the cosmic rays, but certainly it's not above the lead. Okay, this is some examples already published. You can see this spectrum here to compare with the Crab nebula in green. You see those sources actually is quite strong. Okay, for example, like the 1825 minus 1326, which is highest, strongest source we measured according to their flux. So if we are looking closely, we can get such an idea. We believe the cosmic ray origin, but never been confirmed before for SNRs above the 1 TeV. Now we have this window totally open up to 1 PeV. However, according to whatever we measured so far, seems to be the energy is not really high. Certainly, it's not reached to 500 TeV. It's something probably below 100 TeV. This is something we learned from Nozzle's measurement. The other thing, like the pulsar nebula, for example, like a crab, is getting really exciting because we found the 1 PeV photons already measured from a crab. And this is very much a challenge to how to accelerate such a, if it is electrons, okay? Because this energy is already reached to something 2 to 3 PeV for the electron or positrons. So this is really a challenge to us. But as we already saw, probably we need some kind of a hydraulic component to explain, to understand the spectrum better. Now the question is that, is this kind of a flux of the protons with such a small component at a very high energy, are they sufficient to be responsible for the cosmic ray flux above the knee? This is a really interesting question we are trying to answer. For example, like this is the spectrum we already measured at Tibet at the by using Argo experiment plus the telescopes. We found that this spectrum is already there. So we try to understand if this is flux above, certainly above this knee, probably is coming from this kind of pulsar nebula. The other very interesting thing is that we also measured quite of very high energy gamma rays from, for example, like a Cygnus region. Okay, here we know we have many this kind of young massive star clusters, and the highest energy we measured so far is from this very nearby the OB2. So this is probably is really interesting. At least now, as a 1.5 or 1.4 PeV photons is already found from this direction. But this region, the morphology is really complicated. So currently, we still not published this result yet, but very detailed study is ongoing for this cocoon region. We are going to make this measurement. But anyway, we're going to publish this result very quickly. Okay. As I said, the transportation of cosmic rays is really important. Here we don't have very much input yet as the bridge between the cosmic ray accelerators, for example, like these pevotrons, and also the detectors on the Earth. So we have to deal with this, the transportation of cosmic rays nearby the accelerators here. Probably we have targets, we have clouds, we have many things should be put into the simulation. We have to deal with the propagation interstellar here. We have clouds, we have many things, magnetic fields, and also vicinity of the solar system give us more, the complications by this nearby stuff. So let's look into. However, Lasso probably can give us something to help. For example, because this detector is so big, so we can make the anisotropy measurement, so very larger scale anisotropy or medium scale anisotropy study like this. So very helpful. Okay, this kind of cosmic rays measured for this nearby build, the magnetic field probably is really interesting stuff. Another thing is that we have a diffuse gamma ray measured in our galaxy as well. This result is going to be published soon as well. So now we have the idea how much the cosmic rays actually are propagate through our galaxy to generate this diffused gamma rays. And we found very high energy diffuse gamma rays as well. And the flux is already measured. This result will be published soon as well. Okay. And near the source, actually, something really interesting, so-called the pulsar halos. And those guys probably can give us the idea about the cosmic ray the propagation very nearby the source. Maybe the environment there is quite different from what we thought before. Okay, this is the something published on the physics review letter already about the this pulsar halos. As I said, the cosmic ray spectrum is very important once we tried to build up this kind of a propagation program to try to do the simulation of the cosmic rays interstellar and also nearby environment. Eventually, we should have something to compare with this calculation, and this must be the spectrum of the cosmic rays. Now, above the 100 TeV, because we have many measurements for one shower, just like the spectrometer to measure the particles in the collider. So we probably have some handles now to try to do this composition measurement as well as we want. And then once we have this multiple measurements of the shower parameters, we try to separate the pure proton. And for example, like a proton plus helium, and certainly we can get the ion separated. So we probably, at least we have this three types of spectra measured. And also all of these measurements will cover the energy range around the needs. The proton needs now we know probably below 1 PeV, but what the need for the ion is very interesting stuff. And for this kind of telescope, we can reach the energy resolution about 15%. And we have many parameters to measure. For example, like a muon content, and also X maximum by using Cherenkov telescopes. And we can use a water Cherenkov detector to measure the energy flux very near the source, the course of the shower, and also other parameters by using the telescopes. So that gives us, some very good chance to do this separation of the composition. Putting in mind that once we reach the high altitude at 4,400 meters above sea level, the depth of the atmosphere is something around 600 gram. So that is the height is almost perfect for the energy around 10 to the 15 to 10 to 16 near the shower maximum. So that's actually minimized the fluctuation of the event by event from shower to shower. Okay. The something else I want to mention is the absolute energy scale. This is really important. I will show you later on. Here, let's go through this very little bit more detailed. This result, first, the energy range is about pure for the is a 0.1 PeV. This is 100 TeV to 10 PeV. The range we try to cover is the Lie region of the proton spectrum. Okay. Here we can use this as mentioned many parameters to do this separation of the composition. for proton, or pure proton, which we can get to something, the purity greater than 90% of the protons, okay? And once we have this proton samples, then we can do the energy measurement much better, because now there is supposedly there is no pollution from the other composition contributions. So energy resolution, we try to reach the 15% level. And to try to separate helium, it's really, really difficult. It's almost impossible. However, once we have the measurement of a pure proton, then we can measure this kind of a proton plus helium. The hope is that probably we can see at the energy, the twice of the energy of the knee of the proton, probably we can see some kink here. For example, now by using 6 telescopes plus WCDA, the water Cherenkov detectors, and also the outside the ground array, we already have the exposure of the 750 meters, 750 hours data already collected. So unfortunately, this result has not been analyzed well yet. So here is still the prediction. If we put this number on this the spectrum we already measured, then we would expect that here we already have this proton plus helium, something like 5,000 events here. And even beyond the knee, we still have something like the 1,700 shells here. So my hope is that around this region, maybe by using so many events, we probably see some structures here, very interesting. Then that gives us the idea about the need of the helium. Okay, this is the first energy region. And now this detector becomes not only 6, now it's 18 telescopes are built. And now we put this in the circle I just showed as a full circles, full coverage of the directions and the azimuth directions. And then we can use this to reach the aperture of the 82,000 square meter of steradium. So that means we can measure the energy range well above 10 to 7 GeV, which is 10 to 16 EV. So we hope we will see the ion spectrum there with the knee. So the purity of the ion is pretty high, reached to something like 87% for the ions. So we hope we can see the knee very clearly here. Depends on where the knee of the proton is, with the prediction shows that if the knee of the proton is below the 1 PeV, we will be lucky. Then we have a 3 years measurement can make this very clean measurement of proton, the ion needs. But if the need of the proton is still above the 1 PeV, then probably we should have 5 years to make this spectrum like this. Okay, to find the need of the ions spectrum. But anyway, within 5 years, we should have this kind of answer. The very exciting part for this measurement is that, we have this, the long-standing problem of a cosmic ray indirect measurement is the energy scale problem. Because we don't have a test beam to test our detectors, okay? Eventually, for this kind of measurement, we figure out the way by using the magnetic spectrometer between the moon and the Earth, which means we can measure the shadow of the moon by using the ground ray detector. For example, like this water Cherenkov detector. That gives us, the very clear measurement of the shift of this shadow because of the geomagnetic field. So once we have this kind of measurement, then we know the cosmic ray particularly if we can do the separation of the composition, for example, like a pure proton or proton plus helium, and then we can make the prediction of how big of this, deflection will be by using the very good model of the geomagnetic field. Then we can do this kind of energy scale measurement. Unfortunately, this is a very, very precise measurement that requires a lot of statistics. Currently, we publish this result in the Physics Review D by using 8 months of data by one of the water Cherenkov detector array. That reaches the 30% of the uncertainty here, you see? Okay, now we try to use the Cherenkov telescope to measure the energy better than the ground array. However, the Cherenkov detector cannot look into the moon, too bright. So we have to have a sort of the, propagation of this energy scale from this is the measurement. The black is measurements by water Cherenkov detectors. And then we use a common trigger event by this Cherenkov detectors, water Cherenkov detectors, and the Cherenkov telescopes. Of course, no moon. Okay, if we can do this kind of a separate, this kind of a common trigger event, you see this is the energy reconstructed by Cherenkov telescopes. They are very close, and then we know the energy scale. Okay. And this currently, the uncertainty is dominated by the statistics of this very precise measurement of moon shadow location at the high energy part. So this is very exciting. We'll eventually reach the energy level of the 21 TeV. This is the highest energy people reach to do this kind of calibration. So this number will reduce once we have much better statistics within 4 years, for example. This uncertainty will reduce to below the 10%, like this. So that will be very nice. So we know the energy is really calibrated at something around the 30 TeV, and we try to measure the spectrum, the need of the spectrum, proton spectrum around 700 TeV. Okay, so this is the closest energy we can do the calibration. Okay, let's see if we can do something beyond the Milky Way. For example, like this Fermi bubble. Okay, and now we know the Eurosata actually see even bigger bubble here. So this is something we really want to do the measurement. Fortunately, we can see a part of this northern sky, the northern part of Fermi bubble, but we will see a lot of part of this Eurosata bubble. So we can try to understand, by using this multi-wavelength measurement of these bubbles to try to get the better understanding about the origin of these bubbles. Okay. And also people trying to do the detailed simulation of this to generate the bubbles, okay, including cosmic rays put into the simulation. Probably we can improve our knowledge about this bubbles. Oops, so, yeah. AGN and the gamma ray burst. This is something also very exciting to us. Now, we already have the measurement of the AGNs reached a very, very high energy, okay? Certainly above the 10 TeV from our measurements. For example, like a Macarian 421. So that opens quite a very interesting region, window to explore how those guys accelerated the particles at such a high energy. Okay, this is certainly very interesting stuff. M87 is one of the sources we are really interested, but currently we have the measurement only in the very low energy part by using the water Cherenkov, not yet by this ground array at the very high energy part. But anyway, this is something interesting to us. GRB. Currently, this detectors of Lasso can do only the follow-up measurements. In the near future, we are going to set up for the alert as well, because the field of view of this detector is quite large, and by using this 20-inch tubes in the water pools, actually we can push down the threshold energy to something like 100 GeV and even lower, to, for example, like 70 GeV. So this is the way we're trying to get the energy, the gamma ray burst measured. Because this detector is working 24 hours, any moment, so the importance of this detector is that probably once we catch the 1 GRB, we will know the very important information at the T0, or even below, even before the T0. We can get some information back by using the recorded cosmic ray data. The last point is the dark matter search. And this detector has a very large field of view, okay? So this, at least something around 20 dwarf galaxies is actually seeing our field of view of these detectors. For example, this is the list. And this detector has a much higher threshold energy. So at the moment, we did the calculation already for this 1 square kilometer detector. At the energy above, certainly above 100 TeV is the highest sensitivity in the world for this kind of dark matter search. Once we have currently not yet done yet, once we finish our analysis of water Cherenkov detector, this energy threshold will be down a little bit to the something like above 10 TeV. Our sensitivity is still the highest to do this kind of search. Okay, this brings me to the summary. Basically, the implications with the preliminary results of the Pavotron search. Very strong feeling is that SNR seems to be responsible only for the production of cosmic rays with the energy below 1 PeV. And something else, for example, like the Pulsar 1 nebula and the young massive stars clusters will be very interesting sources to look into. And now the completed answers to those questions requires a lot of data from in this UHE domain. Okay, now we have data, and we have a continuously stream of data will coming within years. I would emphasize that actually we need a lot of the phenomenological study in depth for this, very, very important approaches. For example, like this multi-wavelength analysis was dedicated observation of in X-ray bands, and also a particular for this X-ray, this is band. This is a very important, okay? So we should have a very good collaborations with other experiment, like for example, like ESO theta. And the cosmic ray propagation in the galactic disks is very crucial. Many studies should be done within years by using by getting the help of diffuse gamma ray measurement and the cosmic ray anisotropy measurement. Okay. In the end, we need a very, very precise measurement of spectra of diffuse cosmic rays as well. We hope we can measure this proton plus helium and also ion. Okay. Very exciting, as I said, the absolute energy scales, eventually we can reach the 30 TeV within 4 years. So that's all. my talk. Thank you very much.
Thanks a lot for this exciting presentation and all those exciting results